system design. First, I'd like to introduce your team for today. I'm Mohammed Sirat. I'm the Technical Sales Advisor for Fronius South Africa for the Solar Division. Fronius South Africa is an agency of Fronius International. I'd then like to introduce my colleague, Cyprian Nicolo. He's also a Technical Sales Advisor. He's operating from Fronius International. Then I'd also like to introduce my colleague, David Mongi, who is the Technical Sales Advisor, and he also operates from Fronius International. I'd like to take you through the supported regions for each Technical Sales Advisor for Africa. So if you look at David Mongi, he takes care of the majority of the Eastern African countries, as well as some Southern African countries such as Zambia. Then Cyprian Nicolo, he takes charge of the English-speaking West African countries, such as Nigeria, Ghana, etc. Then myself, Mohammed Sirat, I support all the Southern African countries that are indicated in the green. So that's pretty much all Southern African countries besides Zambia. So if you are an attendee from one of these countries and you'd like to get into touch, please make sure that you contact the correct technical sales advisor for whichever country you do reside in. Okay, moving on. I also like to show you our FSP Plus partners. These are basically Fronius distributors in the sub-Saharan African region, and they are considered as the first point of support. Okay, so they are the first point to purchase a Fronius inverter. So if you want to purchase a Fronius inverter, you have to ask one of these companies for a quote. And if you have an issue with the Fronius inverter, your first line of support is whichever distributor you purchased the Fronius inverter from. Okay. All our distributors also keep spare parts in stock. So as I said earlier on, they're also responsible for technical support. And the advantage of having replacement parts in stock is that we can offer you local service, which is really a big advantage on the market. For South Africa, we have Innomatic Solar and IBC Solar, which are distributors. In Namibia, we have Radio Electronic. In Zimbabwe, we have One Stop Solar. In Ghana, we have Tino Solutions. In Kenya, we have CAT, GreenSpark, Nights Energy. In Madagascar, we have Mother Green. In Nigeria, we have Components and Solutions. Then in Senegal, we have Sonikara. Okay, looking at today's agenda. Today, we're going to focus on the correct design for grid-type PV systems. And this will cover the design, simulation, and construction of a grid-type PV system. Again, if you have any questions during the webinar, please feel free to post your questions on the question tab, and my colleagues will be more than willing to answer those questions. Moving on to PV system design. What's very important during your design phase, which is usually the early stage of a PV system development, is to do the correct planning, so to speak. So with your PV panel layouts, as you all know, you get your series layout and you get your parallel layout. Also, there's rules regarding the best practice for series, and there's also rules regarding the best practice for parallel layouts. Okay, we're now going to look at the series layout. So the best practice is that all modules in series should be the same type of module from the same manufacturer. That's very important. Secondly, never mix panels with different short circuit currents in series. Okay. What is an option to afford you more flexibility in design is that you can mix panels with different voltages in series, as long as they are from the same manufacturer, preferably. What's very important is this writing in red over here. It says that the performance of a solar array is as strong as the performance of the weakest elements. Okay, and you'll get to see why in the next slide. So what I'm showing you on this slide is 3 different layouts. Okay, what's allowed and what is not allowed. Okay, so the green ticks is what is allowed, and the red tick is what is not allowed. Okay, So for example, let's look at the first case scenario. Let's say we have 3 panels, okay? They're 400 watts each, they're connected in series. Each panel has a short circuit current of 10 amps and an open circuit voltage of 40 volts, as an example, okay? We connect them in series, connected to your string inverter, which is located somewhere over here. Then the total voltage per the string will be the voltage of each panel added together. So that will be 40 volts plus 40 volts plus 40 volts, which gives you 120 volts, okay? The total current, however, is not added because it's a series circuit, and the total current will be 10 amps. Okay, fine. What is the total power of the string? The total power, obviously depending on which operating condition it is, but for this particular example, we'll take it to be 120 volts multiplied by 10 amps, and that will give you 1.2 kilowatts, okay? Which is basically the powers added together, as you can see, which is equal to 3 times 400 watts. Okay, this is allowed, and this is what we suggest installers and engineers to go for, is a sort of layout. However, if, for example, you're struggling to get the same type of module from the same manufacturer, and for some reason, you were not able to get 400 watt modules, but you were able to get a 200 watt module and 2 400 watt modules, okay? You can still add them in series as long as the short circuit current is the same, but the open circuit voltage is different, as you can see over here. So here we have a 200 watt module with a 20 volt open circuit voltage and a 10 amp short circuit current. Then the next panel, that's a 400 watt module with a 40 volt open circuit voltage and a 10 amp short circuit current, and so on for the third module. When you do your calculation, if you're going to look at the total voltage for the string, it's going to be your volts added together, so it'll be 20 volts plus 40 volts plus 40 volts, and that gives you 100 volts. Okay, your total current, as I said earlier on, it's a series circuit, so the total current will be 10 amps. If you multiply the 100 volts by 10 amps, we have 1,000 watts, which is equal to your wattage ratings of these modules added together. So these first 2 layouts are allowed, okay? But as I said earlier on, the first one is a more preferred option. The third option is what should never be done in a PV system, but basically what's happening with this option over here, we have a 200 watt module, okay? So the same as in this example, we have a 200 watt module, but the only difference is that the short circuit current is now different, okay, to module 2, and it's different to module 3. So the short circuit current over here is 5 amps compared to module 2, which is 10 amps, and module 3, which is 10 amps. Okay, that's the difference. The voltage, we're going to take the total voltage, that's going to be 40 volts plus 40 volts plus 40 volts, and that gives us 120 volts. Okay, your total current, remember I told you the statement early on, a system is only as strong as the weakest components, and in this scenario, the weakest component in a series circuit is the component with the lowest current, okay, which is 5 amps. Although we have a 10 amp module, this whole string will downgrade to 5 amps. So technically what you're doing is actually degrading your system, and now the total power is 600 watts compared to 1000 watts. Okay, and that's a system degradation of about 40%, okay, which is really bad, should never be done. And this is where I now make this statement over here. The total current is determined by the panel of the lowest current rating when in series. Okay, now moving on, we're now going to look at a parallel layouts. So the best practice for parallel layout is to have all modules in parallel should be the same type of module for the same manufacturer. Never mix panels with different open circuit voltages in parallel. And if you do want more flexibility, you can always mix panels with different currents in parallel. The performance of a solar array is as strong as the performance of the weakest element. Again, the same thing for the series layout also applies to the parallel layouts. Looking at the 3 solar setups for a parallel circuit, for a PV system, what's allowed and what is not allowed. In the first example, we have 3 modules in parallel, okay? If you look at the total voltage, remember in a parallel circuit, the total voltage will be taken as the voltage of the string because they're in parallel. So in this case, the total voltage is going to be 40 volts. Okay, your total current is going to be 10 amps plus 10 amps plus 10 amps. And that's going to give you 30 amps. Because remember, currents in a parallel circuit add up at a point. Okay, so the current here will add up to the current there, will add up to the current there. And that's going to give you 30 amps. Okay, so we take 40 volts multiplied by 30 amps, then we're left with 1,200 watts, which is equal to 3 times 400 watts. Okay, because they're in parallel. That's fine, that is allowed. The second scenario is where the first module is different to the last two modules. So over here we have a 200 watt module compared to a 400 and a 400 over here. The only difference with this 200 watt module is that it has a short circuit current of 5 amps compared to the second module, which is 10 amps, and the third module, which is 10 amps. The total voltage is still 40 volts. Okay, your total current, because remember currents add at a point, so it's 5 amps plus 10 amps plus 10 amps, and that will give you 25 amps. When we put this into our power calculation, we're left with 1,000 watts. This is allowed, it's fine. The third scenario is not allowed. What's happening in this scenario is that here we can see the voltage is different. Okay, so here we have a 20 volt, 10 amp panel. Okay, and because the voltage is different in a parallel circuit, the voltage will be the lowest voltage in the node, which in this case will be 20 volts. Okay, so here we can see our circuit really degrading. Okay, the total current is still going to be 10 amps plus 10 amps plus 10 amps. That's 30 amps. Your total power will now be 20 volts times 30 amps, and that gives you 600 watts. So here we can see the system degradation from 600 watts and 1,000 watts. So that's a minus 40% system degradation just by using a module with a different voltage. Okay, so this brings me to this statement over here, which states that the total voltage is determined by the panel of the lowest voltage rating when in parallel. Okay, moving on. We're now going to look at your PV array design. So the first statement is the number of PV modules in series is calculated by using the following equation. Yeah, so I'm giving you an equation over here, and that states N, which is the amount of modules, has to be less than or equal to VD max, which is your permissible maximum DC input voltage of the inverter. Okay, so this value over here in red is what you get from the inverter's datasheet. Okay, all over your VOC. What is your VOC? It's your open circuit voltage of your PV module. And this value you get from the data sheet of the PV module. Okay, so it will differ from each module on the market. Okay, you multiply that by 1 plus brackets T minus 25. What is T? If you ask, T is the extreme minimum temperature under normal operating conditions of PV module. Okay, and this T value is what you get from the data sheet. Okay, of a module. Then you get kV. Your kV is your temperature coefficient of open circuit voltage of PV module in percentage per degree Celsius. Okay, so this value you also get from the data sheet of the PV module. So all the values in the red is the info you get from the inverter's data sheet, and all the values in the blue is the info that you get from the module data sheet. Okay, this now takes us to the third equation over here. So with this equation, it's telling us that the amount of modules that you have in a system should be greater than your MPPT min and less than your MPPT max. Okay, that's important. Okay, moving on. Once you already planned your panels, you've seen what voltage will work in the string, etc. The next thing you need to decide on is the correct solar panel orientation. So a general rule is that PV systems in the northern hemisphere should have their panels facing true south. PV systems in the southern hemisphere should have their panels facing true geographic north. Okay, remember, geographic north is different to magnetic north. So don't make that mistake of pointing your panels, for example, if in the southern hemisphere, to magnetic north. You need to point it to geographic north. For the southern hemisphere, if more energy is used in the mornings, then the panels should face northeast. Okay. And if more energy is used in the afternoons, then the panels should face northwest. Okay. However, if you have your power being used constantly throughout the day, and if you are located in the southern hemisphere, my recommendation is that you just point your panels true north. The next important factor is the angle, and the statement states that the angle of a solar panel should be set as to produce the most energy in a given year, and this is determined by the geographical latitude. A general rule for optimal annual energy production is to set the solar panel tilt angle equal to the geographical latitude. Okay, so let's use an example. Let's take Cape Town. If you look at Cape Town's coordinates, it's about 33.9 degrees south, okay? That's your latitude, and then about 18.4241 degrees east, that's your longitude, okay? So here your latitude is therefore given as minus 33 degrees because it's south, okay? Hence, the ideal tilt angles for panels installed in Cape Town, for example, should be 33 degrees pointing north as a recommendation, okay? Okay, moving on, what's the next important factor for designing the DC side, so to speak? That would be obviously the DC cabling size. As you know, if you incorrectly size your DC cables, you can have a lot of losses in your system. And besides that, you can also spark fires, for example, if your cables are too thin to handle the current coming through from the panels. So I made 6 statements. The first statement states that the current carrying capacity must be equal to or greater than the current to be carried per string or for the system. A good suggestion is to always size for 1.25 times the nominal current of the system. So let's say per string, my nominal current of my string is 10 amps. I should always size my current on my wire to carry 10 times 1.25. So that would be 12.5 amps. Okay, that's what's called a safety factor. The third statement states that we must be able to withstand environmental conditions. The reason for this is that solar panels are usually located outdoors. Well, they're always located outdoors, and they're in the environment. So they have to deal with irradiation, shining on them the entire day. They have to deal with rain, etc. So we have to make sure that the cable we use is applicable to the environment. Statement number 4 states that special attention needs to be paid to the voltage drop, which increases with cable length. So again, you don't want to have your cables to be necessarily too long, because the longer your cable is, the more voltage drop you have. Again, this leads to system degradation. The 5th statement states that consideration has to be placed on whether the cable is stranded or solid core. Okay, so if you have a stranded cable, it can usually take more current than a solid core for the same diameter. That's only one of the advantages. So if you look at this picture over here, I'm showing you what a stranded core cable looks like. So here we can see we have strands in a DC cable. Then if you look at this image over here, this is a single core. So this is where we have a single core DC cable. Now, if you look at the gauge of the wire, and let's compare, let's take trying to think of a good example here, but let's take a 8 gauge wire, for example. That can carry, about 40 amps. Okay, that's a stranded core. Whereas a single core, a thicker single core cable, which is 10 gauge, can only take less amps. So this is why I said earlier on, if you use stranded cable, you can carry more amps for a thinner diameter cable. Okay, that's where the advantage is. Moving on to the next statement, this states that the specific resistance of the cable has to be considered. And in order to get the specific resistance of a cable, you need to refer to the data sheet of that cable, or to the material characteristics of whichever material you're going to use. So for example, let's say if you are going to use copper, copper usually has a specific resistance of around 58 multiplied by 10 to the power of 6 Siemens per meter. Okay. Then if you look at aluminium, aluminium has a specific resistance of around about 36.59. Okay. This is very important in order to calculate the amount of acceptable power loss you're going to have in your system. So if you look at these 2 equations over here, it states that power loss is equal to I squared R. So you as the system engineer, you need to decide how much loss is acceptable. Is a 1% loss acceptable to your client, or is a 10% loss acceptable? Hopefully you say a 1% loss is acceptable. So if you take 1% of a system size, let's say we're dealing with a 100 kilowatt system, 1% of 100 kilowatts is 1 kilowatt. So in this case, your P loss will be 1 kilowatts, and that will equal to I squared R. Your I will be the amount of current, the maximum current that's being carried in your cables, and that will be squared and multiplied by R. Okay, how do we get R? That's a good question. We get R from this equation over here, And R is basically obtained from 1 over your specific resistance multiplied by L will be your length of the cable. So this is the length of the cable from the inverter to the modules, okay? And we use these equations in order to work out the area. Okay, so once because remember we get the power by taking the percentage of the total system that's an acceptable loss. We use this to calculate the resistance. We put the resistance in this formula, and then we use the value of sigma, which we have over here, and we already have the length. We know the length, but we just want to calculate the area. What is the acceptable area? We will then get a value for the area. So in this example that I did over here, the area worked out to be 1.5 millimeters square. Okay. Then if we refer to the wire sheet, what is a 1.5 millimeter square cable? It's a 16 AWG cable. And then this is the sort of cable you need to purchase if you want to have a 1% loss on this sort of a system. Okay, I will now be launching a poll. I really appreciate if everybody could please share their inputs. Okay, the question is, what is the most important parameter during design for best DC yields? Do you think it's the inclination of panels? Maybe you think the direction of panels is more important, or maybe it's a DC cable sizing, or maybe it's having the correct string planning. I really appreciate it if everybody could please share their answers. Okay, I will keep the poll open for about another 15 or 20 seconds, so please share your inputs. Okay, thanks for sharing your inputs. I'll now be closing the poll. And I'm now sharing the results. So again, you can see the majority of the audience today believes that correct string planning is the most important factor to yield the best DC. I also agree with that. That is the most important. So followed up by directional panels, and thirdly by DC cable sizing. Okay, thanks for sharing your inputs. Okay, I will now be handing over to my colleague, Cyprian, who will now take you through the middle half or the middle of the presentation. Cyprian?
Yes, Mo, thanks a lot for your detailed presentation. So I will be continuing with system design using two configuration platforms. That's the Solar configurator, the Fronius Solar configurator, and the Tauro configurator. I want to believe you can all see my screen now and hear me clearly. Mo, if you could please come back on and confirm if you can hear me loud and clear.
Yes, all good, Cyprian.
Okay, great. So let's continue with this part of the presentation. So Solar configurator basically is a free software or application that you can use to have your dimensions done easily. So it basically entails, as you can see, of three major parts. That's a section for the PV module selection, and then the inverter selection, and then general settings. So that's basically how it's made up of or constituted, as you can see. So you have the freedom to choose whatever PV module. And I must say here that these modules are based on what we get from the manufacturer, and they are periodically updated on our platform. So after that, you can now make a selection of the inverter, the Fronius inverter you intend to use for your design. Then after that, you can now make the general settings. Here, you can now include if you're doing it, if the design includes storage or without storage, and then select your annual power consumption, and then select your load profile. So we will have a look into Solar configurator and then see how all this play out. Okay. Yes, I'll just read in a question from, so please continue to send your questions, and my colleagues will, of course, attend to them. So let's continue with the presentation. Great. So at the end of the day, after configuring, which we're going to see in the subsequent slides, we're going to have something like this. This would now help us to choose the particular orientation or the what our system will be constituted of. So here you have, say, let's pick a particular column and then expatiate on it. So now let's look at what this particular column has to say. So the first part gives us the number of modules and the inverter ratio. As you can see, for this particular design, it entails that we're going to be needing 32 modules. And then the inverter ratio in this case is 101. Inverter ratio simply is the ratio of the DC side, the capacity of the DC side as against the capacity of the inverter. So yes, you have, of course, you're free to select storage capacity. So you can select storage capacity, but then there's, of course, a recommended or an optimate storage capacity, which will be shown or given to you during your system configuration. That's using the Solar configurator. Then beneath it comes different arrays possible that you can achieve. So here you have PV1 1 by 20 and then PV2 1 by 12. This simply means that on PV1 you will have one string of 20 modules connected in series, and then on PV2, PV input 2, you're going to have one string of 12 modules connected in series. So that's what this basically means. So don't worry, even if you don't understand it now, we're going to look at it more, have a more in-depth look. So from these respective columns, if you select any box or any orientation, it's going to pop out with all the information about this particular specification. It gives you all the respective coefficient values, be it MPP voltage at STC, same with the power. As you can see, shows you or tells you if string fuses are required or not. And the beautiful thing about this is you can actually have the PDF version of it. So by clicking on Create Report, it's going to generate a PDF version of this same report for you. So you can actually use it as a tender to your clients. So, like I said, we are going to have a demo, let's say. So, in order to do this, I would have to go through it together. So, I will. Let's go through it together. So you can start by selecting this link here. Of course, you're going to have the presentation, so you can do it on yourself. Copy this link and then paste it on your web browser. We're having a bit of glitch. Okay, there we are. So if you now paste it on your web browser, it will now take you directly to the Solar configurator, as you would see pretty soon. It's taking its time to load. There we have it. So with this, as I have shown you earlier, you will be able to configure your system. So let's now take from here, like I told you, you can select your module. Your module manufacturer. So Jinko tends to be a more kind of a popular Sorry, this is taking time to load, but it will eventually. So once it does that, you can now select the module type you want to make use of. Preferably, you could make your selections from this. So Jinko, I believe, have up to, 500. So let's scroll to that and see if we can have something like that. Great. So let's see. Let's just take an average. Let's take the 535 watts panel, and then let's come to this part of the inverter selection. If it's here, you have the choice to make choose this particular inverter series that you want to make use of. Let's go for SIMO. And then once you select SIMO, it will now give you all the series of the SIMO that are available. So let's take the maximum, which is the SIMO 20 3-phase. So after doing that, you can now select if you're going with, the annual power consumption, depending on your region. So with this, you can now see that it has already presented us with different arrays that is possible. And if you look here, you can actually, from here, you can actually increase the inverter ratio. If you want to go for the 150 ratio, which of course, if you all know, our inverters are can be over dimension up to 150%. So as you keep on adding this, you now continue to get adjusted scenarios or adjusted specifications that you can use. So there we have it. You can now move to the right and then select the best scenario for you. So as we can see here, we have different selections based on the inverter ratio. So let's go for the highest inverter ratio available here, which is a 147%, which will entail us using 56 modules. And then how these modules will be oriented, there you have it. So you can now, let's say, select this particular one. So once we select this, it's now going to give us all the information we need about this particular selection. It tells us that we're going to have 2 strings on 1 MPPT. Each string will contain 16 modules each. So by so doing, you will now have a good idea of how your panels will be oriented. So going back to the presentation, great. So going back to the presentation, with the selection I have made, it entails that you're going to have 2 strings containing 16 modules each. So I deliberately did this so that you have a better or good understanding of how these will be oriented as per connection to your inverter. So once you have this, you're going to have 2 strings comprising of 16 inverters each connected to the respective MPPTs, as you can see. 16 by 2, and then of course 12 by 2. In this case, to have 12 modules connected on the times 2, as in 2 strings connected. In this case, 2 MPPT2. So that's how this is done. So you can see that with the use of the Solar configurator, you can conveniently configure or design your system, and of course, taking into consideration the information given to us by my colleague, Mohammed. See that in the previous slides. So let's take a look at the system design with the Taro configurator this time. Okay, so before we do that, I'll just have to run you through, for those that don't know, Taro is our latest product, which is specifically designed for large commercial installations. We have 2 variants, the Taro Echo D and the Taro Echo P. So that's for the Taro Echo. Now, Taro Echo D, as the D tends to suggest, is meant for direct connection. In this case, you can connect directly to the inverters, as can be seen here, and then you can now travel with a long AC connection cable to your AC panel. Then for the Taro Echo P, P tends to suggest for pre-combined connection. So it is pre-combined using DC junction boxes or DC combiner boxes, and then you can now travel with a larger diameter of DC connection or DC cables to your Tauro inverter, and then go with short runs of AC cables to your distribution panel. So that's the main difference between the D and the P. So the D is also called the decentralized topology. It is decentralized because the inverters are sort of in a decentralized orientation, distributed all across the connection or the modules area. So of course, as you can see, it's connected near to the PV modules. You have longer runs of AC cable and then additional AC combiners and different cable diameters necessary. So, but for the P version, which is also called the centralized topology, the inverters of the system are placed near the feed-in point, as can be seen, because you already have collected the DC voltages or energy from the modules and then transported via DC connection to the Tauro inverters, as can be seen. And then a special attribute, because I'm going to shed more light on it in the subsequent slide, is that you can actually achieve AC-DC chaining of inverters from the AC side, of course. So it, of course, helps with reduction in BOS costs. So you can actually have up to 4 Tauro inverters, 4 50 kilowatts Tauro inverters AC-DC chained, and then, of course, 2 Tauro Echo 100 AC-DC chain, meaning that the maximum you can go is 200 kilowatts. So for want of time, I would have to say rush through some parts of the presentation. So for AC-DC chaining, this is basically how it can come in as a very, very important factor in terms when it comes to your inverter selection. As you can see, instead of taking individual AC cable runs from your inverters, you can actually daisy chain your inverters and go with one single run to your AC distribution box. So, like I promised, we're going to have a brief run of the Tauro configurator. So to do this, I'll still have to end the presentation so that we can copy the link and do the same thing as we did in terms of the Tauro configurator. So you can open a new page and then paste it. This will now take us to the home page of the Tauro configurator, where we can now do our configuration using the Tauro. And mind you, same thing can actually be applied on the Tauro configurator, because we have actually integrated the Tauro configurator into it. So I'm just going to take you briefly through this and then still touch on how you can do this on your Tauro configurator. I will be a bit fast about this. So from my previous presentation, I believe I've taken examples of the centralized version. So let's take the decentralized version in this case. So if you select this centralized variant, you will now have to make a selection of the particular inverter you want to use. Let's take the Tauro Echo 50. Once you make a selection, you now have to go to your fuse selection and listening, or if you remember from what Mo said, the current carrying capacity must have to be greater than the current being carried. So as you can see, that is what is actually explained here. You can see that we have 15 amp fuses and 20 amp fuses. All this depends on your string current respectively. So as you can see, for 10 amp fuses, you go with 15 amp fuse, and then for 12 amp, for 10 amp module current per string, you go with 15 amp fuse, and then for 12 amp module current per string, you go for the 20 amp fuse. So depending on your string module string current, that would now determine which string fuse you're going with. So if you select, let's say we select the 20, you now go to the next stage, which has to do with the surge protection device, the SPD. Usually, we tend to, depending on your region, you can select the SPD type 1+2. Type 1+2 basically gives you lightning current arrestor and the voltage arrestor. Type 2 only gives you over voltage protection. So if we go with one, type 1 plus 2, it now takes you to the AC connection area. Now, this is very important. If you're using a multi-core cable, you would have to select this particular variant with this article number. If you're using single core cables, as you can see, this could be for the 3 line voltages, L1, L2, and L3, and then ground or neutral, you would have to go with this particular variant. Then if you're using AC daisy chaining, you'd have to go with this particular variant. As you can see, we have 10 openings here, 5 for the outgoing, and then 5 for the incoming. So that's how you make your selection for the AC side of your inverter. And then once you have done that, let me select the AC daisy chaining option. You now have to go for the AC disconnector. So here you have the indication that you don't have the option for AC disconnector because of the AC daisy chaining, because there will be enough space to implement the AC disconnect switch. So if you select either the single core option or the multi-core option, you will be able to have AC disconnect possible. So that's how you do your configuration on the Taro configurator. Now, going back quickly to the Solar configurator, like I told you, it's possible to do your configuration, Taro configuration here. As you can see, select Taro, go to, let it finish loading, okay. So you can now, as we have previously selected, we selected the Taro Echo D. So let's select it here once again. And then it would now automatically take us to possible orientation. So mind you, this is for inverter ratio of 116 max, as indicated here by default. So you can actually push this up to say 150, because our inverters, of course, can be oversized up to 150%, as earlier said. Once we're able to get to that value, we can now have selections that are possible with this particular inverter ratio. So the maximum inverter ratio we can get here, according to the string current, is a 4/17 string multiplied by 2. So meaning that inverter input 1, as in the PV input 1, would contain 4 strings of 17 modules each, and then the inverter input 2 will contain 4 strings of 17 modules each. So going straight back into the presentation to give you an illustration of how this would look like. Okay, so we're talking about the Taro 50D. So this simply means that you're going to have 4 strings, as you can see in this case, 1, 2, 3, 4 strings each containing 17 modules to PV input 1. And then we're now going to have another 4 strings of 17 modules each on PV input 2. So that gives you a general idea of how the system can be utilized. So on the final note, this is a representation of how this can actually look like. So zooming into this, we can see that this is an implementation of a Taro 50D connection. As you can see, the string, first of all, the inverters are connected close to the inverter, close to the modules, and then you can see the DC strings coming in and connecting directly to the modules, and then your AC coming out. This is obviously an AC daisy chained orientation. As you can see, the AC cables coming out from this inverter, coming into this one, and then going out through this. So this specifically is a very, very good design, and of course saves costs eventually. And yeah, so this brings me to the end of my presentation. I will be handing over to Dave for the next or the following part of the webinar. But before I do so, I would be launching the poll, and of course, I'll be expecting you all to please give your respective responses, because they will be really appreciated. So I'm going to launch the poll now. So the question is, which PV simulation software do you use most often? So we have options like the Helioscope, the PV-systems, PV-Sol, manufacturer's software, and others. So please, we'll be glad to have your feedback in this regard. I will be leaving the poll question for, let's say, 10 more seconds from now, and then we'll be collecting your responses and sharing it with you. Okay, thank you very much. I'll be closing the poll now and sharing it with you. Great. So 43% go with helioscope, 21% go with PV-systems, none go with PV-Sol, 7% uses the manufacturer software, while 29% uses others. Thank you very much for your response. As I now hand over presentation rights to my colleague, David Mwangi, who will be continuing from this point. David?
Yes, thank you so much, Cyprian, for your section and exciting information that you have shared with us regarding simulation tools that are available at Fronius. I will now be going through the construction segment of this webinar, and the key idea of this section is to give us some hints on the actual installation of the system and how we can avoid some common mistakes that might occur from time to time when you're doing the actual installation in the field. So let's get started and look at what a typical system layout looks like and how you can identify, even before you start planning for your system, which components need to be taken care of. So in this layout, we can see that we have the inverters as well as the PV modules, which make an essential part of the entire PV system. However, we also do have things like meters and data communication components, which are also equally important and come into play once the entire system is installed. So just going quickly is to indicate that starting from the PV array, we are also talking about the racking system that has to be considered when you are designing your system, and also the lightning protection of the system in general. So one keynote here is the fact that lightning protection in most cases for commercial and industrial applications is already existing for the building, but you have to consult with the concerned lightning engineer in terms of if that would be sufficient enough also to cover the support structures or the racking system that has been used for the solar system. Also, we talk about the DC cabling, and here we are talking also about the DC combiner boxes as well as the surge protection devices that are integrated, can be inside the inverter or outside of the inverter. And also, coming to the inverter itself, we talk about the data communication, which is a critical area as far as integrating a system with several inverters is concerned, that each inverter must be able to communicate to the other regarding what is going on with the control system. Also, the internet connection goes through the inverter to be able to check how the system is performing from time to time. So just give me a minute. I need to be able to switch something off here. Sorry about that. Okay, so let's continue. So as we can see here, we are also going into the AC cabling section, whereby we talk about the AC combiner boxes as well as the surge protection for the AC area. And lastly but not least, also the metering of the system. Here we are talking about both the grid meter as well as the Fronius smart meter that is contributing to measuring consumption and giving you data for comparison with production of the system. However, for you as an installer or a designer of the system, you need to come up with the actual system layout once you have considered all the elements that need to come into play for your installation. And this will be a typical system layout. So it will show what will be the positioning of the inverters from plus all the modules or the strings that are going to be connected to the inverters. It will also give you an idea at a glimpse of how many inverters are going to be used into the system, and how this PV system on this side is going to be interacting with the existing power supply system for that particular premises or customer. So in this particular example, we can see, for instance, we have at least 3 diesel generators that are in this system. We can, in addition, see what are the channels for Modbus communication, as well as internet connection through Modbus TCP as well, and CAN bus, which will be the communication for generator controllers. So this kind of schematic for the actual system layout is very, very important. And in the long run, it is going to help you to avoid a lot of troubles before and during the installation. In the installation, you are, of course, able to specify all the components that are going to be needed for your installation. And this can be used as a briefing tool for your technicians and other installers to be able to know what exactly the desired system is going to look like in the end. So let's now look at a few installation hints that would be very helpful once you start now the actual construction of your system. And to start with, we look at the PV array as well as the racking system. And one of the key highlights, or one of the key things that is very common with commercial and industrial PV systems, is the fact that modules are typically roof mounted. And these are done using special built structures for as far as mounting structures are concerned. However, we have to be aware of the mounting recommendations from module manufacturers, which are the recommended orientations and stuff like that. What kind of clamping can be used. Also in the design phase, shading effects, especially for tilted modules, need to be addressed. So especially if you're working with complex roof structures, you probably are going to go near chimneys and stuff like that. There are some simulation tools that are going to also additionally be able to help you simulate how these are going to have an effect on your yield or production of the PV system. In general, also your structures must be able to withstand both uplift and downward forces. And these mostly will come from wind, in most cases in the African market, but also let's say considering Europe and some parts of the Southern Hemisphere, maybe parts of Cape Town, snow can also be a major concern as far as loading is concerned on the rooftop. So when you're doing your system, you have to also consider how much load that particular roof is able to carry. And then additionally, look at sealing all the penetrations that have been caused when you are drilling in for your mounting system or the racking system. And then of course, as far as the PV array is concerned, the interconnection between panels, you have to make the use of appropriate interconnectors as well as provided tools or recommended tools. So most modules nowadays for commercial systems are supplied already with MC connectors with a minimum cable length at the back. And this can be used directly without any modifications to form a string that is connecting one panel, positive and minus, all the way to the end of the string. And of course, module interconnections have a huge impact on the DC power delivered to the inverter, as we'll see later on. So this gives us also a glimpse of the kind of crimping tool as well as MC4 tools that would be required when you're doing an installation for the PV system. As far as the DC cabling is concerned, as already discussed at the beginning by my colleague, you have to ensure that all the cables are designed to carry the expected current plus a margin factor. So some of the common mistakes that you can avoid is in some cases you can have a completely installed system, looks very good on the roof, but some strings are not connected properly. So this can be quite hard to identify, especially if you're using centralized inverter designs or in large systems. And therefore, it becomes a lot of painstaking work for you to be able to identify which exact strings were not interconnected. So also, it's possible for reversed string cables, which can eventually be a cause of damage to the inverter. So the problem can be overcome by clearly labeling all the concerned wiring on the DC side as well as the DC strings. Another common mistake would be when you swap the strings. So it can happen that the plus and minus of unrated strings are matched. So it becomes very difficult to trace in a big system. So in this case, this is possible also to use the wrong series of parallel strings at the connection of the inverter, especially if you consider that an inverter like a Fronius Simo or Fronius Echo, you can connect up to 6 strings directly to the inverter. So This one, as already mentioned, you have to be very careful with how you label your strings to be able to know which plus and minus are coming from which strings, so that these are not mixed up at the inverter level. So regarding the connectors that are used, especially the MC4 plugs, some of the major installation mistakes would include poor crimping, especially when you have to add more MC4 plugs into the system. And this also comes from using the wrong kind of tools. And eventually, this will cause a lot of overheating and potential for fires later on in the system. Also, connectors can be exposed to moisture for several reasons, and eventually also this becomes problematic for the performance of your system. You can imagine that you are undertaking a system, but at some point you have to stop the installation process, but the MC4 plugs are left exposed on the roof. So if it happens to rain for whatever reason, and then the installation continues at a later stage, there is a bit of moisture that is going to be trapped unknowingly to the installer in the MC4 plugs, and this eventually will be a cause of failure for the MC4 plugs themselves. Another common mistake would be when the connectors are not properly latched, and over time, this will also be a cause of arcing and a potential source of fire for the overall system. In terms of resistance on the DC side, there are areas where you can have very high resistance on the DC side. But when you check the voltage using a multimeter or a voltmeter, everything seems okay until the inverter wants to draw current from the PV system. So once the inverter draws current from the PV system, then the voltage drops immediately and the inverter shuts off. So this becomes also a very tricky area to troubleshoot when you are considering all the faults that can come from the DC area. So one of the causes would be improperly latched connectors or loose connections when you're talking about especially the DC combiner boxes. This can be caused by damage also or manufacturing defects in the solar modules, whereby you have excessively high resistance on the DC side. So overall, ensure that the DC cabling is done very, very neatly, and use cable trays and sufficient labeling, as already mentioned, to make that sure that you don't encounter as many mistakes. When it comes to the connection of the DC side to the inverter, talking about the Fronius project inverters, you can connect up to 6 strings directly to the Fronius SIMO, for instance, SIMO 20, or the Echo inverter. And in some cases, you might need to use a DC connector kit, especially once DC combiner boxes come into play. So in terms of the string connection, what I'd like to give you as a hint here is that for a direct connection into the inverter, this is possible for the strings to come directly into the inverter. And then if you have multiple strings as well, and the inverter is capable of handling this through 2 MPPTs, you can bring all the strings directly to the inverter, depending on whether your actual installation conditions are met. If, for instance, you want to have a DC combiner box integrated into the system, and you're going to use a SIMO 10, Fronius SIMO 10 to 20, which have multiple MPPTs, therefore, all the string plus and minus are first of all pre-combined before they come into the inverter. Then what you have to take special care of is that when you're doing the initial commissioning of the inverter, you put your MPPT to off position, because this MPP2 number 2 will not be active at this point when the input here has been pre-combined using a DC connector kit. And that applies also for the smaller inverters with multiple MPPTs. So once the DC connection area has been pre-combined, MPPT number 2 has to be switched off. This is just an overview of the overvoltage protection. I think we are pretty much familiar with the OVPs that are available or possible with Fronius inverters. So as I said in the beginning, this is also an important part of the system when you're thinking about the damage that can be caused by lightning. So properly installing the SPDs or the OVPs is very, very important. In terms of the AC cabling, you have to ensure that all the AC cables are correctly sized for current. This is the starting point and is very, very important. So possible concerns with AC cabling as far as potential faults are concerned could be grounding problems. So when you have materials that have different galvanic properties being used in the grounding system, So this is something that you have to be very aware of, that if you have a mixture of maybe copper and aluminium in your grounding system, this could potentially cause a corrosion at some point in the future, and therefore your grounding system does not work very well, and this might actually, in the long run, cause the inverter to fail. In cases whereby you are using some enclosures that are painted, maybe enclosure boxes that need to be grounded, and you have to scrape the paint off, this is a hint, or use what are referred to as paint cutting fasteners. A proper earth rod is of course necessary, and depending on your soil constitution, you take the necessary resistance measurements to make sure that the earthing or the grounding connection to the earth rod is at the required or recommended levels. So also a typical challenge with the AC side with the high resistance as seen with the DC side. So when you measure the grid voltage, this seems okay. But when the inverter tries to export power into the grid, then it encounters a challenge. And this is, of course, a failure that is also relatively challenging to diagnose, because everything seems okay when you measure with a multimeter. So it's very, very painstaking. And therefore, the thoroughness of the installation process and making sure that everything is properly tainted up is very, very important. So this high resistance causes the voltage to rise once the power or the current reaches a certain point that has a loose connection, and this inadvertently also causes the inverter to shut down. So this one of the main causes, as mentioned, is a loose connection. As we can see with this connection here, on one side it was quite loose, and eventually a lot of overheating and overall damage, complete damage of this connector. So AC breaker problems also, it's important to select the breaker for the right system current. So in some unfortunate events, you have a breaker that is failing either in the open or closed position. So this becomes a very high risk factor, especially for installers when you're doing your maintenance work, because you could be thinking that you have already closed down this particular or opened this particular breaker, but in actual sense, the breaker is still passing current through, and therefore it becomes a high risk for the welfare of the installers and all others concerned. So always make sure that you actually test with an appropriate tester, that there is no current available or there is no voltage going through the lines before you proceed with your installation or maintenance works. In terms of cable terminations, also a big potential source of errors, especially when there are many cables or the cables are too big. This is where you have to ensure that the right torque is used and applied, and also be careful with the stranded cables. I know my colleague mentioned that stranded cables would be able to carry slightly more current for the same cross-section diameter, but you have to be very careful with stranded cables, because when the cables are very near to each other, you could have some strands over jumping to the next phase or neutral, and this of course creates a problem for arcing, and this is not something that is desirable for a system's safety and operation. Over time, of course, all cables will loosen up, so you have to plan in your operation and maintenance proper retorquing procedures to ascertain or to make sure that all the relevant termination points have the relevant required torques applied. In terms of the actual connection, when you come to the inverter, the Fronius Tauro inverter gives us very good possibilities for AC termination using the V clamps. And using the V clamps, you're able to connect anything from 35 millimeter square up to 240 millimeter square. So the cable lugs in this case would only be required for the ground connection. And one key special attribute about the V clamps is that you can flip it over when the cable diameter is changing. For cable cross sections that are bigger than 185 millimeter square, you can see the profile of the V clamp. And then to be able to securely tighten cable cross sections from 35 to 150 millimeter square, then you can easily push this out and flip over the V clamp for it to be able to securely position the cable within the inverter. So a few tips also regarding the inverter section. What you should be very, very careful about is that you have to observe keenly all the installation recommendations. And these will include making sure that the mounting area can bear the full weight of all the inverters that are in the system, especially if all the inverters are mounted in the same area. Make sure that the spacing is adequate, and this means that there will be proper circulation of air, as well as ease of service when the inverters need to be serviced in future. No direct sunlight exposure, especially for the Fronius snap inverters. I know we talk about them being IP65, but they are not immune to direct sunlight. So unless otherwise specified, like with the Tauro, because the Tauro design is very, very unique. It has a double layered front cover, and that enables the inverter even to operate at the direct sunlight. But for all other inverters, the snap inverters used for project systems, we do recommend that they are built within a shed to prevent early derating behaviors. And therefore, these are the possible choices for both the Tauro as well as the snap inverters. And these are available, of course, in the Fronius user manuals and installation guides. Another key, very important aspect when it comes to your inverters in the system will be the inverter to inverter communication. What we have said, if you have a system that has more than one inverter, then the inverter to inverter communication must be clear. And of course, with the Fronius snap inverters, in this case, we are talking about the Fronius SolarNet ring. Other mechanisms, especially for the Tauro inverter and the Gen 24 inverters, can be used because these inverters for now are not able to communicate inverter to inverter. So if you're going to do a big system using the Fronius Tauro inverters, we can recommend other alternative plant control mechanisms other than just relying on the SolarNet ring from Fronius. If there is a failure in the communication loop, this of course can cripple the entire system. And most failures in operation are actually caused by communication hiccups. So because in snap inverters, maybe you find that the termination plugs are missing on the edge of the communication loop, or the cable itself is broken. And this of course can be avoided if you keenly observe all the recommended installation procedures by Fronius. Then in terms of the Fronius SolarNet ring itself, what I would like also to mention here is the fact that by using the Ethernet cable in combination with the RJ45 sockets, you can extend this ring for a distance of up to 1 kilometer or 1,000 meters. And of course, we know that the Ethernet cable is limited to a max distance of about 100 meters before the signal starts degrading. But when you look at the inverter.com area, then the inverter in and out section, when you're connecting the RJ45 sockets, acts as a signal repeater, and therefore this allows the distance to go much longer, even up to 1,000 meters for the entire SolarNet ring. In terms of metering, also a very important section of the system. So a typical system will of course have 2 meters. It will have a grid meter that is already there provided by the grid operator. And then of course the Fronius smart meter that is checking or regulating feed-in limitation and obeying other national codes as far as PV systems are concerned. And also in terms of looking at the profitability of the system, the Fronius smart meter allows you to check what is the consumption of the system overall versus production. And therefore, is the system going to be profitable in the long run or not? And this data is of course available through Fronius SolarWeb for monitoring. So there is a communication, of course, that needs to be established between the Fronius smart meter and the data manager. And possible errors that you need to be aware of as far as the Fronius smart meter is concerned is very common missing termination resistor. And a lot of installers in this case would think that the smart meter is not actually working, but it's only that the termination resistance is not activated, either at the Fronius data manager or at the Fronius smart meter itself. Another common mistake would be the use of wrong cable types. So we recommend for the connection of the smart meter to the Fronius data manager, the use of only twisted pair of a Cat5 cable. And then also check out that the insulation at the edge of the twisted pair. So you can see here the stripped edge of a Cat5 cable and an unstripped comparison here. So ensure that the installation is very thorough and you don't have any chances whereby the Modbus connection between the smart meter and the data manager is done with an unstripped Cat5 twisted pair connection. So of course, in this case, there will be no possibility of establishing a connection. Also ensure that the twisted cable pairs are not twisted on the other end, as there maybe could be 4 or 5 pairs inside the cable. Ensure that you observe the color codes as provided with the Cat5 cable. Another important hit, as well as far as the smart meter is concerned, we have already talked about the termination resistance of 120 ohms that must be done from the smart meter side. With the new smart meter series from Fronius, you can achieve this by only bridging terminals, but with the older series of smart meters, you actually need a physical resistor to be attached to the Modbus connection between the smart meter and the data manager. So one highlight here is, of course, that once you are doing the Modbus connection from the smart meter to the data manager or the pilot, the maximum distance that you can cover is not more than 300 meters. So if you have situations whereby you think you're going to need to run the cable for more than 300 meters, then we encourage you to talk to us and look at what are the other possible alternatives for connection between the two. As far as the settings of the smart meter are concerned, very, very simple. On the 63 amps smart meter for residential use for single and three phase, only the address, as far as the Modbus address, has to be set in the smart meter as well as the data manager user interface. And then for the 50 kilo amp or the 5 kilo amp, the new smart meter series, it is required that you set correctly at least the transformation ratio of the CTs, as well as the transformation ratio of the voltage transformers. Also, you might need to change the password on the smart meter itself, and the guidelines are very well detailed in the user manual of the smart meter. For the selection of the current sensors, we also do recommend that you pay particular attention to the CTs or current sensor that you're going to put in your system. And one of the key highlights here that we can talk about is the assembly of the CT itself. You have the possibility to use either a rigid or a hinged CT. So rigid CTs are usually cheaper with better power and accuracy levels. And rigid therefore means that is a CT that needs to go through a cable. It has no possibility of opening. But a hinged can be installed even when a system is operational without interrupting the voltage. So if you encounter situations whereby it's not possible to disconnect power fast for you to be able to install a CT, the most ideal solution will be to go for a hinged solution that comes with screws. So you can open up one side of the CT and then you clamp it and screw it over the particular cable. In terms of system commissioning, the inverter therefore becomes the control and operational command center for the entire system. And all the system functionality may in error be associated with the inverter. So the inverter will, in most cases, send alarms as well as error messages to Fronius SolarWeb. And these error messages could be inherent inverter errors or errors from other components within the system. So these errors could, of course, come from the PV and DC side, the datacom area, as far as the Modbus, for instance, connection from the inverter to the smart meter is concerned, or the inverter to inverter connection. It could be an AC side error when you have surges and stuff like that, or loose connections. And also environmental factors, maybe a lot of heat in the particular area of installation and things like that, as well as neglect, whereby people neglect to follow proper operation and maintenance procedures. So ensure that always you follow installation recommendation thoroughly, and this makes the commissioning process easy and smooth. Also, when you are done with the installation of the system, we do recommend that you create a checklist for all the areas of the system, starting from the DC side on the modules, the strings, the DC cabling, DC combiner boxes if used, then come to the inverter, all the way to the smart meter and the connection point for the grid, and ensure that everything that needs to be done before you commission the system is done. And this allows you to avoid a lot of errors and mistakes during the commissioning phase. Then, of course, you go to the actual commissioning for the particular inverter. You go to the data manager for the snap inverter, and then the Tauro and the Gen 24 are going to go through the pilot user web user interfaces. So after everything is properly verified and after commissioning, then you can bring the entire system online, and therefore means that the system starts producing power and injecting it into the grid. As far as monitoring is concerned, this allows for operation and maintenance of the system, even remotely. And the monitoring portal has to be available for about over 99% of the time. So any planned maintenance and schedules on the monitoring portal must be communicated with installers well in advance so that they're able to plan themselves. And the monitoring portal should also be API compatible. So if you look at all these attributes, we are basically describing what is available with the Fronius Solar Web portal. And of course, we are very familiar with how to connect our systems into the Fronius monitoring portal. So I don't have to go through those details. In the very end, you have to think about, once you have done the installation of the complete system, the actual system data documentation, which is very, very important. So we have things like owner information. Be very careful about that you have documented these details, the names of the owner, the location, or contact information, email as far as phone numbers. So it makes it very easy for future correspondence with your customers. In terms of the system itself, you need to be able to record all the data that is concerned for the system. What is the design model, nominal design power, installed DC capacity? What are the module parameters or details, including the manufacturer, model, and quantity? What is the inverter? Who is the inverter manufacturer, in this case, Fronius, the model and the quantity that you have in the system? The racking system specs, including the model as well as the quantity used for the racking system. And this allows for proper operation and maintenance in future, so should something go wrong or requires to be replaced. Also very, very important, something that you should never ever forget with your systems is to take as built photos. So in the beginning, you have the actual system layout as it appears. But if you look at this photo here, probably the actual system layout was not able to show these inverters in this kind of position. So in future, if you have problems maybe with the dust or heat exposure for snap inverters, you can be able to go back to your photos portfolio and check exactly how are these inverters installed, so that now we are starting to experience problems with heat exposure. So it's very, very important that these photos are able to show your PV array, your inverters, cabling, as well as the switch gear as installed. So very, very important for you to remember that. So, and that basically brings us to the end of the webinar today. But before we end, I would like to give you some further information regarding useful sources of information from Fronius. So you can go to fronius.com download section, a lot of information there for installers and designers. Also, we have a lot of YouTube resources for how to install systems, webinar recordings, a particular dedicated playlist on YouTube for the African region, whereby we post all the webinars that we do. Therefore, we do invite you to access these webinars over there and familiarize yourself with all the different aspects of Fronius systems. And with that, we basically have come to the end of our webinar for today. So I'd like to thank you all for taking your time to be with us for today's webinar. And also extend my thanks to my colleagues Cyprian and Mohammed for their presentation. And we do look forward to welcoming you next week for another training. But for now, goodbye and enjoy the rest of the day.